Alright, I'd like to discuss a problem on calculating ionic strength. So you may know the concentration of ions or ionic compounds in solution, but you want to be able to compare solutions with multiple ions or ionic compounds to each other in terms of the ionic strength. This can help you figure out things like osmotic pressure, or consider how multivalent ions affect the ionic properties of a sample of fluid, okay, compared to monovalent ions. So for this we have a Debye-Huckel approximation that the ionic strength I is equal to 1/2 times the sum of the concentration of species I, right, all species, times the charge squared of that ion. Okay, so for this example, we were told that we have 0.15 molar for potassium ions. So we will have 1/2 times 0.15 molal, this is 1 squared, so I'll give these some notation, K plus. It's important that you know what the ion is, right, including your polyatomic ions. If you forgot those ones from general chemistry, it's always a good time to use Google. Okay, then we have 0.01 molal for sodium ions, so that's another 1 squared for Na plus. And then we have 0.04 molal for magnesium ions. So now we need a 2 squared here for our Mg2 plus. And finally, 0.12 molal for hydrogen phosphate ions. So this one is going to be, so we have a HPO4 2 minus. Remember, phosphate is PO4 3 minus, hydrogen phosphate is PO4 2 minus, and dihydrogen phosphate is PO4 1 minus. Okay. Yeah, here we go. Okay, so we have a 2 here. And we can go ahead and put charge symbols in. So you can have the negative sign, but notice that since these terms are squared, you really only need the absolute value of the charge in order to compute this. So if you go ahead and plug all of these things in, then you will get that the ionic strength of this is 0.40 molal. Okay, now the thing that I want to point out is that you need to consider the concentration of the ions. So you could be given these in some ionic compounds. So let's just make up a sample problem instead, where perhaps you are given that you have 0.1 and let's say millimolar. So I also want to point out that this can be in molality, this can be in molarity. Okay, you can use any term. I suppose if you didn't exceed 1, you could even consider some mole fractions or something. Anyways, you need some concentration term. As long as it matches between the different ions, you can sum them. Okay, so it can be used with molarity or molality. I believe that Jim Allen's book gives this in molarity, but if you Google many other resources, it will give it with molality. Molality may be practical if you don't know exactly how much water you have. You can take the mass of a solution and then you accurately have the total mass, as opposed to, I suppose, having to know exactly how much water you have without the ionic components taken into consideration. Okay, so we have 0.1 millimolar. Let's say that we have now some potassium phosphate, so K3PO4. And I want to know what is the ionic strength of this. Remember that means I will have totally 0.1 millimolar of this compound, which will dissociate into 3K plus ions and a PO4 3 minus anion. So that means that I'll have 3 times 0.1 millimolar, or 3 millimolar potassium ions, and then 1 times 0.1 or 0.3 and 0.1 millimolar for a phosphate anion. Okay, so when we put this into our ionic strength equation, then we want to consider the total concentration by imagining these dissociation reactions, or I recommend actually writing them out for yourself because you will change the concentration of the ions compared to the compound itself. So this problem will not look exactly like the homework problem that you were assigned where you're already given the exact ion concentration. And beware, especially the most challenging problem will have the same cation or anion in multiple compounds. So you will either want to enter them as multiple terms or consider the total concentration that you have. If you have 2 things with potassium, then you would have even more than 0.3 millimolar. Okay. So now we can say that I is equal to 1/2 times 0.3 millimolar times 1 squared plus 0.1 millimolar times minus 3 squared. And so we have a 0.9 millimolar ionic strength solution.